Okay, let's unpack this. We have a pretty formidable stack of sources today.
They really do.
And we're going on a deep dive into the very, very foundation of modern mathematics.
Right.
We're not talking about algebra or calculus here. We were tackling the crisis points, the mind-bending stuff about infinity, the limits of knowledge, and what mathematical reality even is.
In our analysis, it's leaning really heavily on the work of Joel David Hamkins.
A key figure.
Oh, absolutely. For anyone in mathematical logic, set theory, especially if you follow the discussions on, say, math over flow, Hamkins is just essential.
He's a legend there.
He is, and he specializes in these exact questions.
Mm-hmm.
The strange sizes of infinity, the paradoxes that kind of broke the system, and this eventual realization that, mathematics might not be one single thing.
But like a multiverse of different realities.
Exactly, a multiverse.
So our mission today is to give you a shortcut to understanding these, just colossal paradigm-shifting ideas.
A very big task.
It is. We want to get some clarity on the discoveries that forced the greatest thinkers of the 20th century to question if truth and proof were even the same thing. It's a journey to the bedrock.
And that journey really begins late 19th century with Georg Cantor's transformative and, frankly, revolutionary work. He discovered something that seemed completely impossible.
Which was?
That some infinities are demonstrably bigger than others.
And the reaction to that was intense. Our sources show this wasn't just some abstract mathematical dispute.
No, not at all.
It caused this huge philosophical, even theological uproar. For centuries, infinity was tied to the divine, right?
Right, the oneness of God.
So the idea of multiple sizes of infinity, it was seen as an insult.
Yeah.
And leading mathematicians, like Leopold Kronecker, they just vehemently rejected it.
It kicked off a true mathematical civil war.
To really get why, you have to look at the history of infinity itself.
Yeah, you really do. Think all the way back to Aristotle. He made this distinction between potential infinity.
The idea that you can always just add one more.
Exactly. And actual infinity, which is a completed, finished, infinite set. Aristotle just rejected the actual infinite. But Cantor embraced it.
And we see the problem illustrated so clearly even earlier with Galileo's paradox. You take the natural numbers 1, 2, 3, and so on, and then the perfect squares 1, 4, 9.
Okay.
You can just match them up 1 to 1. You match n to n squared.
Right. And this 1-to-1 matching, we call it being equinumerous. It suggests they're the exact same size.
But Galileo was really troubled by this because the natural numbers obviously include the squares, plus a whole infinite bunch of other numbers.
2, 3, 5, 6, all the non-squares.
How could a set be the same size as just a small part of itself?
So that's the conflict. That's the tension right there.
You've got the modern Cantor-Hume principle, which says size is all about that 1-to-1 correspondence.
But that smashes right into Euclid's principle, which everyone took for granted.
The whole is always greater than the part.
Exactly. And Cantor's genius was just accepting it. For infinite sets, he said, Euclid's principle fails. The whole can be the same size as the part.
So he resolved that tension.
He did. He showed how two sets could be equinumerous, but then, and this is the key, he proved that the set of all real numbers is not equinumerous with the natural numbers. He found a bigger size.
Okay, before we get to that bigger, uncountable infinity, let's try to make the first one, countable infinity, a bit more palpable.
Hilbert's hotel.
The famous thought experiment, Hilbert's hotel. This is the size that matches up 1-to-1 with the natural numbers.
Right. So imagine a hotel, rooms 0, 1, 2, 3 forever, and it is completely full. Every single room has a guest.
Not a single vacancy.
Then a new guest arrives. The manager doesn't panic. They just make an announcement.
What's the announcement?
Everyone, please move from your current room N to room N+1.
And suddenly room 0 is free.
Magically available. The hotel is still full, but you've added one more person. It shows adding one doesn't change the size.
Which is such a great illustration of how Euclid's principle just breaks down. But we can push this absurdity, right? An infinite bus pulls up.
An infinite bus. Seats 0, 1, 2, and so on. Also completely full.
How do you fit another countably infinite set of people into a full hotel?
The manager uses a clever trick. The difference between even and odd numbers. They move all the current guests to the even rooms.
So guest n moves to room 2n.
Right. Instantly, all the odd-numbered rooms are now free.
And the infinite bus passengers can just fill those odd rooms.
You've just fit 2 infinite sets into the space of 1.
Okay, now for the final test. The ultimate challenge for countable infinity.
Hilbert's train.
An infinite number of train cars, and each car has an infinite number of seats. An infinity of infinity.
It sounds hopeless. It really does. But the solution, it relies on one of the most fundamental ideas in all of number theory.
Prime factorization.
Prime factorization. The manager just needs two parameters, the car number, C, and the seat number, S. They assign the passenger to room 3 to the power of C times 5 to the power of S.
Wait, okay, why 3 and 5? Why not just something simpler, like C plus S?
Because C plus S, that could give you the same room number for different passengers. Like, car 1, seat 10 is 11, but car 10, seat 1 is also 11.
Collision.
A collision. But by using powers of unique prime numbers, like 3 and 5, you guarantee that no two pairs of car and seat numbers will ever produce the same room number.
Because every whole number has only one unique prime factorization.
Exactly. So every single passenger gets their own unique room.
That is just... It's a brilliant application of number theory. And the key takeaway here for you listening is just crucial.
Mm-hmm.
You can put together countably many countable sets, the hotel guests, the entire infinite train, and the result is still only countably infinite.
It's an incredibly resilient size of infinity, but now we have to leave that countable realm.
On to the real numbers.
Yes, the real numbers, all the numbers on the number line. That includes the rationals, fractions, and the transcendentals like pi and e.
And it's weird, because even though the rationals they're dense, right?
Yeah.
You can always find another fraction between any two fractions.
Infinitely dense. But they are, by that same Hilbert's train logic, still only a countable set.
So if the fractions are countable, how did Cantor prove that the entire set of real numbers is a strictly larger size of infinity? How did he break through that wall?
He used the diagonal argument, and it's maybe the most celebrated proof in all of mathematical logic.
High praise.
It is. He focused on the real numbers just between 0 and 1, represented as decimals.
Yeah.
And he said, okay, let's assume, for the sake of contradiction, that we could list all of them.
We could put them in a big list, R1, R2, R3, and so on.
Exactly. If you can list them, they have to be countable.
And then he goes and proves that any such list has to be incomplete.
Precisely. He constructs a new number, we can call it Z, that cannot possibly be on that supposedly complete list.
How?
By moving down the diagonal of the list. For the first digit of his new number Z, he picks a digit that's different from the first digit of R1. For the second digit of Z, he picks one different from the second digit of R2, and so on. For the nth digit of Z, he makes sure it's different from the nth digit of Rn.
I see where this is going.
Right.
Because this new number, Z, it's different from R1 in the first position. It's different from R2 in the second. It's different from every single number on the list in at least one spot.
So it can't be equal to any number on the list.
Which means the list wasn't complete after all. A contradiction.
A contradiction.
Yeah.
And that proves the real numbers are uncountable, a larger size of infinity.
Wow.
And what's really fascinating is that this idea, this diagonalization, it became more than just a proof. It became a fundamental tool, a template for revealing limits and paradoxes that gets used again and again.
And that productive turmoil, Cantor's discovery plus the power of diagonalization, it forced this massive rethinking.
It led directly to the foundational crisis.
The mathematicians realized they needed a rigid, safe structure to build on. And that led to set theory.
Set theory became the lingua franca of mathematics. A set is just a collection of things viewed as one abstract thing. But the key question was, what collections are you allowed to form?
And that need for safety was really driven home by Russell's paradox.
Yes.
Which used that exact diagonalization logic to just attack the naive early ideas of a universal set. You can't just collect everything.
It's like the difference between people and committees. For any group of people, you can always form more possible committees or subsets than there are people. That's a basic fact.
Right.
So now, apply the paradox to that. Let's say we try to name every possible committee after a person.
Okay.
We went into an impossible committee. Let's call it Committee D. It's the committee of all people who are not on the committee named after them.
I think I see the trap.
The contradiction is immediate. Let's say there's a member, Daniela. Is Daniela on Committee D?
Well, if she is on Committee D, then by definition, she's not supposed to be on the committee named after her, which is Committee D.
So if she is, she isn't.
And if she's not on Committee D, then she fits the rule for membership and she should be on it.
So if she isn't, she is. It's a complete logical collapse.
And the consequence of that is just stunning. The class of all sets can't be a set itself.
It can't. It showed that if you let people form sets without any rules, you get contradictions. And that's why mathematicians needed the rigid rules of ZFC.
Zermelo-Fraenkel set theory with the axiom of choice.
Right. ZFC gives you these 9 tightly controlled axioms, these basic rules that say which collections are safe to form.
Like the axiom of infinity, which basically just confirms that Hilbert's hotel is mathematically sound.
It does. It formally asserts that an infinite set exists.
But then you have the really famous one, the axiom of choice, or AC.
What?
By far the most controversial axiom in ZFC.
It really is.
So what does it let us do that's so contentious?
It says that if you have any collection of non-empty sets, even an infinite one, you can always choose exactly one element from each of those sets.
Okay, that sounds reasonable.
The controversial part is, you can do it even if you have no definable rule for making the choice.
Ah, this is the socks and shoes analogy.
Exactly. That makes it so clear. Imagine an infinite number of pairs of shoes. A butler can easily pick one shoe from every pair. He just says, I'll always pick the left shoe. That's a rule.
Makes sense.
But now, imagine an infinite collection of pairs of identical, indistinguishable socks. There's no rule. You can't say pick the left sock. They're identical.
There's no way to define the choice.
Right. And the axiom of choice just asserts that the choice function exists anyway. It asserts existence, not our ability to construct it.
And this whole push for formal foundations, it brings us to the ultimate challenge to mathematical certainty.
Kurt
Gödel's incompleteness theorems, which just...
You-
They shattered the optimistic program of the great mathematician David Hilbert.
Hilbert had this immense faith that mathematics was this perfect, complete structure.
His program had 2 huge goals, right?
2 colossal goals. First, create one single strong axiomatic theory, like a perfected version of ZFC, that could answer all mathematical questions.
And second,
Prove that this strong theory was totally consistent, free of contradiction, using only simple, absolutely certain finitary methods.
and Gödel in 1931 proved both of those goals were impossible.
Utterly impossible. His first incompleteness theorem proved that any sufficiently powerful, self-consistent axiomatic theory, like the one you need just for basic arithmetic, will be incomplete.
And incomplete means what exactly?
It means there will always be true statements that you can neither prove nor disprove from within that system. The system can't prove everything that's true in its own world.
So mathematical truth is bigger than mathematical proof.
It is. And then the second incompleteness theorem delivered the final blow to Hilbert's second goal. It proved that no such powerful theory can prove its own consistency.
The rules of the game can't prove that the game itself is safe.
Exactly. It's like a used car salesman telling you he's trustworthy just because he says so. You need outside evidence.
So this is the crucial distinction that really underlies this whole deep dive.
It is.
The gap between truth, what is objectively the case, and proof, our finite step-by-step path to knowledge. Gödel proved that gap is permanent.
And we can connect this to computation using another diagonalization argument, the halting problem.
Right. The question is there a universal algorithm that can look at any computer program and tell you for sure if that program will eventually stop or if it will loop forever?
And we know the answer is no. And the proof, again, uses that same self-referential contradiction that we saw with Russell's paradox. The same pattern. Assume, for contradiction, that a halting procedure exists. You could then build a contradictory program, let's call it Q.
Okay.
When you feed Q's code to the halting procedure, if the procedure says Q will halt, then program Q is designed to just loop forever. If the procedure says Q will loop, Q is designed to immediately halt.
It always does the opposite of what the prediction is.
It always does the opposite,
Right.
which proves the procedure has to fail. The halting problem is undecidable.
And that undecidability ties directly back to Gödel.
It does. If a complete axiomatic theory of arithmetic existed, it would be powerful enough to solve the halting problem. It could just prove every true statement about which programs halt.
But since we know the halting problem is impossible to solve,
Then such a complete theory must also be impossible.
so now we get to the most famous unanswered question left over from all this. The continuum hypothesis, or CH?
Hilbert's #1 problem in 1900.
Right. If the natural numbers are the first size of infinity and the real numbers are a bigger size, is there anything in between?
And for decades, it just defied every attempt. And then in this dramatic sequence over 2 generations, the answer was found. But it wasn't the answer anyone expected.
First was Gödel in 1938.
Right. Gödel proved that the continuum hypothesis is consistent with ZFC. You can't disprove it using the standard axioms.
But that's only half the story. 25 years later, Paul Cohen comes along.
And he invents this completely revolutionary technique called forcing.
To attack the problem from the other side.
Exactly. Cohen used forcing to build an alternate mathematical universe where the negation of CH was true. And he proved that this alternate universe was also totally consistent with ZFC.
So I guess you can't prove it's true and you can't prove it's false.
You can't, which means CH is independent of ZFC.
And what does that independence really suggest about mathematical reality?
It leads directly to this set-theoretic multiverse view, a pluralist perspective that Hamkins really champions.
The idea that there isn't one true set theory,
but rather multiple equally valid, self-consistent mathematical universes. In one universe, CH is true. In another, it's false.
And forcing, Cohen's tool, is basically the way you travel between these different universes.
It's the map maker. It shows what's possible in other mathematical realities. And what we find is that practically every non-trivial statement about infinite sets is independent of ZFC.
So finding an independent statement isn't a failure.
No, it's a discovery. It's a discovery about where the natural joints are in mathematical reality. It forces us to ask, well, what criteria should we use to choose which universe is the real one?
Which plunges us right into the deepest philosophical waters. If mathematical reality can be plural, what's more real? This abstract math or the physical world we live in?
Well, a lot of structuralists would argue that only the relationships between mathematical objects matter, not their substance. We don't care what a number is, just how it behaves.
Okay.
But I would actually argue that abstract mathematical existence is, in a way, clearer than physical existence.
That sounds provocative. How so?
We can give a completely precise definition of an abstract object, like the empty set. It has 0 members. We know exactly what it is. But the reality of a physical object, say, this table,
It gets fuzzy.
it gets more and more mysterious the deeper you go. Is it the atoms, the quantum fields, string vibrations? We hit these profound unknowns almost immediately. We can fully describe the set, but the table remains a mystery.
So I think the biggest takeaway from this whole deep dive has to be this realization that mathematics isn't some finished monolithic thing.
Not at all.
It's a dynamic, growing realm that's defined as much by rigorous progress as it is by this perpetual mystery at its core.
And if we have to leave you with one final idea, let's go back to Cantor's positive legacy, the transfinite ordinals. This is maybe the most beautiful system he ever created.
Counting past infinity.
Counting past infinity. You count all the natural numbers, and you reach the first infinity, which he called omega.
But the ordinals don't stop there.
No, you just keep counting. Omega plus 1, omega plus 2. Eventually you get to omega plus mega, which is omega times 2.
Yeah, on and on.
All the way up to omega squared, omega cubed, omega to the power of omega. It's this beautiful structured system for counting through different levels of infinity, and it's the basis for so many complex instructions.
So in the end, the core lesson we took from Gödel is still the most powerful one.
I think so.
This distinction between truth, the objective state of mathematical reality, and proof, our finite, rule-bound way of getting knowledge.
And that permanent, unabridgeable gap, the space between what is true and what we can formally prove, that's not just some curiosity for logicians. It defines the limits of our understanding in any complex system. And it should urge you to constantly question the foundations of what you know, even when those foundations feel like absolute bedrock.